In this lesson, we're going to show that every linear transformation has a matrix associated with it, and we're going to find ways to compute the matrix of a linear transformation. Formally speaking, every linear transformation T going from Rn to Rm can be written as T of V is equal to AV for some unique matrix A, which is m by n, and a vector V inside of the input space Rn. Let's start with an example from the last lesson. Here we have a reflection, which is taking a vector v1, v2 inside of R2 to another vector v1 minus v2 also inside of R2. Our goal is to show that T of v can be written as a matrix A times the vector v. To do that, we begin by rewriting this linear transformation. T acting on the vector v, which has components v1, v2, gives a vector v1, negative v2. Now the goal is to write this as A times v1, v2 is equal to v1 minus v2. And now let's find the matrix A by inspection. So we're going to find a 2 by 2 matrix such that when it multiplies the vector v1, v2, it gives an output vector v1 minus v2. It should be easy to see that the first row of the matrix A is 1, 0, and the second row is 0, negative 1. We say that this matrix is the matrix associated with the following linear transformation. Now let's consider another example. Here we have a transformation T going from R4 to R3, where the input space is R4 and the output space is R3. We are asked to construct a matrix A of the transformation such that the following definitions are given. We are told how the matrix acts on specific input vectors. First, T of 1, 0, 0, 0 is 2, 3, 1. T of 0, 1, 0, 0 is negative 2, negative 3, negative 1. T of 0, 0, 1, 0 is negative 3, negative 2, negative 2. And T of 0, 0, 0, 1 is 0, 5, negative 1. If you have not noticed already, these vectors right here are simply the standard basis vectors for the input space. And the vectors on the right-hand side are the output vectors, which are a result of the transformation acting on the given input vectors. It is customary to label basis vectors by the letters E. So E1 would be the first basis vector, E2 the second, E3 the third, and E4 the fourth basis vector for the input space R4. Note that this is just notation and we are not giving any new information right here. Remember that our goal is to construct a matrix of this linear transformation. So let us begin by considering any vector in the input space R4. Now any vector in R4 is going to have 4 components. Let's call them v1, v2, v3, and v4. This vector v can be easily expressed in terms of the basis vectors that are given here. So we can write it as v1 times the first basis vector, v2 times the second basis vector, v3 times the third, and v4 times the fourth. Note that this is only possible because the basis vectors happen to be standard basis vectors. If these vectors right here had not been standard basis vectors, these factors right here would not be v1, v2, v3, and v4. They would be something else. But for now, let's stick with standard basis vectors. Using our notation above, we can write this expression as v1 e1 plus v2 e2 plus v3 e3 plus v4 e4, where the vectors e are the standard basis vectors for R4. Our next step is going to be to take T of the vector v and write that equal to A times the vector v. So let the transformation T act on the following vector v right here. From the previous expression, this gives that T of v is equal to T of v1 e1 plus v2 e2 plus v3 e3 plus v4 e4. Now recall from the previous lesson that T acting on a linear combination like this one becomes V1 T of E1 plus V2 T of E2 plus V3 T of E3 plus V4 T of E4. But T of E1 is given by the vector 2, 3, 1. T of E2 is given by the vector negative 2, negative 3, negative 1. T of E3 is given by this vector, and T of E4 is given by this vector. So now we can replace these expressions with the given vectors. And so we get the following relation. Remember that this linear combination can be written as a matrix times vector, where the columns of the matrix would be these vectors right here, and the vector which the matrix multiplies would have components v1, v2, v3, and v4. So here is the resulting matrix multiplying the vector v1, v2, v3, and v4. And this is simply equal to A times V, where A is this matrix right here, and it is the matrix associated with the linear transformation T. The result of the previous example works in general. So if we have a linear transformation T, which is going from Rn to Rm, where Rn is the input space and Rm is the output space, then the m by n matrix associated with the linear transformation T is given by the following. The first column of the matrix is going to be T of E1, the second column T of E2, all the way up to T of En. And these E's, E1, E2, E3, E4, all the way up to En, are in fact the basis vectors for Rn. But they are not any basis vectors. They are in fact the standard basis vectors for Rn. This way of computing the matrix A is only valid if the input basis for the vector space Rn is the standard basis and the output basis for the space Rm is also the standard basis. Now, of course, it is worth noting that these E's are inside of Rn and these E's are inside of Rm. These right here are the columns of the n by n identity matrix, and these are the columns of the m by m identity matrix. Now let's consider an example. Let's take the linear transformation that goes from P2 to P1, where P2 is the set of all polynomials that are of degree at most 2, and P1 is the set of all polynomials that are of degree at most 1. The transformation is defined as follows. T acting on a polynomial p of x gives the derivative of p of x. Our goal in this example is to find the matrix A associated with the linear transformation. Before we can proceed with this, note that the input and output spaces are not Rn and Rm. So how are we going to find this matrix? Well, first we have to choose an input basis and an output basis, and we have to choose those to be the standard bases for P2 and P1. Here is the standard basis for P2, and here is the standard basis for P1. Recall that if we have a polynomial p of x which is inside of P2, then this polynomial can be written in the most general case as a plus b times x plus c times x squared. So we have three arbitrary constants multiplying 1, x, and x squared. Similarly, if we have a polynomial inside of P1, then that can be written as a constant times 1 plus another constant times x. Our next step will be to compute how the transformation T acts on the input basis vectors. We start with T of 1. So T of 1 is equal to 0 because the derivative of the number 1 is simply 0. Then we compute T of the second basis vector x, and T of x is the derivative of the polynomial x, which is simply equal to 1. And finally, we compute T of the third basis vector x squared, which is the derivative of x squared, which is equal to 2 times x. Now the question is, given this information, how are we going to write the matrix of the linear transformation? it's not like we can write A equals t of 1, t of x, and t of x squared. That's absolutely wrong. So this is completely wrong. We're not going to do that. Instead, we're going to translate these expressions into vectors. Let's see how to do that. The first thing to recognize is that this 0, this 1, and this 2x, they are all inside of P1, which means I should express them in terms of the basis vectors of P1. So the basis vectors of P1 are this 1 and this x. So 0 is equal to 0 times 1 plus 0 times x. Now this 1 right here is equal to 1 times 1 plus 0 times x. And this right here is equal 0 times 1 plus 2 times x. So how is this going to help me? What I'm going to do is collect these coefficients right here and place them in a column vector. So first I'm going to get 0, 0. For the second entry, we're going to get 1, 0. So this is a column vector 1, 0. And for the third entry, we are going to get 0, 2. So the column vector is going to be 0, 2. These vectors right here are going to be the columns of the matrix A. So the matrix A has columns 0, 0, 1, 0, and 0, 2. This is it for our lesson today. In the last lecture of this semester, which will be given by your respective instructors, we're going to consider the case of what happens if the input and output bases are non-standard bases. But that's until then. Goodbye for now.